All right, so the last part of the correlation and regression material concerns outliers and two related types of points, influential points and high leverage points. Here we're just going to talk about the idea of an outlier. And so I think I told you when we first brought up the subject that we were going to see many definitions, and we have, right? We've seen that outliers are often associated with points way out in the tails of the distribution, sometimes in the last 5%, 2%, 3%. There's no real solid definition there. It just means points very far away from the norm. And we've seen that sometimes they just look like mistakes or some type of irrelevant point, but sometimes the information is all about the outliers. We've seen on box plots that there is a formula above the upper fence, below the lower fence for outliers. And here's another formula for these regression lines, and that is any point which is 2 standard deviations of the residuals away from the line would be considered is considered an outlier. Now, if you look at the example that we've got here, the only point that could possibly be 2 standard deviations away is the one on the far upper right. Everything else is closer to the line, meaning the difference, the deviation between the actual value and the predicted value for a given value of x. Those are called the residuals, those values. Have to be less than 2 standard deviations. Now where the heck are we going to get those standard deviations? Well, you remember when we were first looking in this series of videos on correlation and regression at Lin-Reg t-test output, it gave you that value s. That value s is the standard deviation of all of the deviations associated with all the points. So let's roll down here and see how we would look for outliers graphically. The way that you would do it is off of the linear regression line, you would draw another line that's parallel but is 2 standard deviations above the regression line, and a third line which is 2 standard deviations below. And it's a simple thing to do. Remember that red line is the linear regression line. It's a plus bx. It is a is minus 34574. B is 18.6. So that line is y is equal to minus 3574 plus 18.6 times x. If I want to raise every point up by 2s, and s is 141, I have to essentially add 282 to the right-hand side of the equation. And I make then another line, which I call y plus, that purple line. That purple line is minus 34574 plus 18.6x plus 2 times s, or 2 times 141, or 282. Likewise, the green line is y is equal to minus 3457 plus 18.6x minus 282. We plot those and then we just check to see if the data points lie within those or if one lies outside it. And you can see the one that we had suspicions about, that point there at 1960-2132, lies just inside the line. So there's no outliers in this data. So let me stop there and come back at the light board to talk a little bit more about this technique. And we'll do the technique numerically rather than graphically. All right, thanks much. All right, so I had originally planned to do this demonstration of identifying outliers numerically on the light board, but it occurred to me it might be better if I use screen capture here and and the TI emulator, because you'll be able to see a couple of things here that I was going to do by hand. And in particular, you're going to see some capabilities of the calculator that we haven't talked explicitly about at this point. So let me get rolling here and turn this thing on. And you'll find that I've already put in list 1 and list 2 the data from the problem that we're interested in here. Here's the years 1870 to, if we go all the way down, you'll see 1960. And at this point you might be remembering some of the data. We started at 340, I think. There it is, 340. And in 1960 that per capita income got as high as 2132, which I could find for you right there, 2132. So what I would like to do now is to use the calculator to find the residuals. The residuals, or the deviations, are the difference between the actual data point and the predicted value, the y-hat values, for any given value of x. So the way I'm going to do that is go up here to list 3, like this, put the cursor up in the header section, and I'm going to write in the formula that I want the calculator to calculate for me. Remember, the residual line was y is equal to a plus bx. A is minus, I better do this like this. A is, let's clear that for a second. A is minus 34574, and B is 18.61, and I'm going to multiply that by every one of the L values. So I'm just going to enter L1. So you can sort of see the code that you're using there. And if the cursor is at the top, when I hit enter, what it does is populate list 3 with all the predicted values. So all I have to do now is get over to list 4, go up into the header, keep trying to do that like that, go up into the header, and now I just have to subtract list 3 from list 2. So I'm going to enter L2 minus L3, and when I hit, there's the L2 minus L3, and when I hit enter, then it populates list 4 with those differences. Now, now we can just examine it, because what we're looking for is any deviation which is greater than 2 times s. S was 141. Any deviation greater than plus or minus 282. And so we just have to look down the list of deviations. The biggest number I see is 125. I now see a 173. If I continue down, the biggest value should be indeed the last one. This was the point on the upper right. It's 230, but that's less than 282. And so there we've examined point by point the deviations. There's no outlier. All right, I hope that's a little helpful.